Hey, today we're going to look at operations on power series, by which I mean how to take a power series, do something to it, and come up with a new power series. And before we jump right in, I'd like to talk about power series in general and how to think about them really. Here's a power series that we've seen before, the sum n equals 0 to infinity of x to the n, which is 1 plus x squared plus x cubed, etc. And depending on the value of x that you plug in, you may or may not get a value out. But if you pick some value of x in the interval of convergence of this power series, then you do get some number. And so you can think of this as a function whose domain is the interval of convergence of the power series. In this particular power series we've seen before, this is the geometric series. We've replaced the r's with x's. And so really, this is just the function 1 over 1 minus x, as long as the absolute value of x is less than 1. So here's a function whose domain is all the numbers between -1 and 1, excluding -1 and 1. It's expressed as a power series. And we actually can compute what the value is when you plug in one of those numbers in the domain of the function. On the other hand, here's another power series that we looked at in our last video, the sum n equals 0 to infinity of x minus 2 to the n over n squared plus 1. And we found that it had an interval of convergence of all the numbers between 1 and 3, including 1 and including 3. And that means that if I plug in an x value between 1 and 3 into this power series, a number comes out. I can't tell you what number like I could in the previous example, this function f of x, the geometric series, where there was this formula 1 over 1 minus x that would actually give us the answer. But in this case, I can say that, if you tried to compute g of 2.5, for example, if you plugged x equals 2.5 into this power series, some number comes out. Don't know what it is. But I do know that you get some precise number. If you tried to plug in 4, you don't. You get infinity. But any number between 1 and 3, you get some number. That makes this power series a function whose domain is the interval from 1 to 3. Okay, what can you do with power series? Well, first of all, you can add and subtract them because you can add and subtract series. As long as their intervals of convergence overlap, you can add and subtract power series. Turns out you can multiply and divide power series. It's rarely done because it's horrible. Just imagine what that looks like. A power series essentially looks like an infinite polynomial. Imagine multiplying two of them together and the distribution that has to happen. Every term multiplied by every other term. So it can be done. You can multiply power series. You can even divide them, which is even more horrible. We won't do too much of that because, as I said, it's horrible. And then there's this theorem. It says that suppose you have a power series that converges on some interval I, then you can multiply the power series by a positive integer power of x. And the reason you can do that is because for any particular value of x, x to the m is just a constant. Imagine the m is 7 and the value of x is 8. Well, 8 to the 7th is a constant. You can multiply a series by a constant, and that doesn't change whether or not it converges. So you can multiply a power series by a positive integer power of x. And the second part of this says, suppose you have some continuous function, you can replace the x in the power series with the continuous function of x, and it will still converge, not necessarily on the interval I, but for all values where f of x is in the interval I. Let's look at a couple of examples. We know that 1 over 1 minus x can be written as a power series. It's the power series 1 plus x squared plus x cubed, etc., and on forever, and that converges for all absolute value of x less than 1. The first part of this theorem says I can multiply that power series by, for example, x cubed. And now I have a power series for x cubed over 1 minus x. X cubed over 1 minus x is x cubed plus x to the 4th plus x to the 5th plus x to the 6th, etc., and on forever. And it converges for all absolute value of x less than 1. The second part of this theorem says I can replace the x with a continuous function. Here I've replaced it with the continuous function 3x. And I get a power series for 1 over 1 minus 3x. it's 1 plus 3x all squared plus 3x all cubed, etc., which simplifies to 1 plus 3x plus 9x squared plus 27x cubed, and on forever like that. And it converges not when absolute value of x is less than 1, but when absolute value of 3x is less than 1. And that's the same thing as saying when the absolute value of x is less than a third. So here's a power series for 1 over 1 minus 3x, and it gives us a function that works for any x value between negative a third and positive a third, excluding the two endpoints. Okay, you try this one. Start with the power series for 1 over 1 minus x, and see if you can come up with a power series for 1 over 1 plus x squared. Use the second part of the theorem here with the continuous function f of x equals negative x squared. So pause the video, take a moment, and see if you can figure that out. And when you're ready, start it back up. And there's really not much to it. You simply replace the x's with negative x squared, and you get this expression here. We should do some simplifying. And we get that 1 over 1 plus x squared is just 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth, etc. And it turns out that the absolute value of negative x squared is less than 1, precisely when the absolute value of x is less than 1. So here's our power series for 1 over 1 plus x squared. And here's our next cool theorem about power series. It says that you can differentiate or integrate a power series term by term. In other words, you can think of a power series as an infinite polynomial. Well, we know how to take the derivative and the integrals of polynomials. It's easy to do. And this theorem says that that does not change the interval of convergence, except possibly at the endpoints of that interval. Starting again with the power series for 1 over 1 minus x, which is 1 plus x squared plus x cubed, etc. This theorem tells us that the derivative of 1 over 1 minus x is the derivative of 1 plus x squared plus x cubed plus x to the fourth, and on and on and on forever. On the left, it's probably easiest to take the derivative by thinking of 1 over 1 minus x as 1 minus x to the negative 1. Becomes a chain rule problem. I'll let you work it through. You get 1 over the quantity 1 minus x all squared. On the right, we're just taking the derivative of a polynomial term by term. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared, etc. And this is true when the absolute value of x is less than 1. It may also be true when x is equal to 1 or x is equal to negative 1. The theorem doesn't tell us what happens at the endpoints. Let's look at another example. We recently figured out a power series for 1 over 1 plus x squared. It's 1 minus x squared plus x to the fourth minus x to the sixth, etc. And it converges when the absolute value of x is less than 1. And so by this theorem, the integral of 1 over 1 plus x squared should be the integral of this infinite polynomial. The integral on the left is very easy. The integral of 1 over 1 plus x squared is just the arctangent of x. On the right, you have to be slightly careful because, when we integrate something, we want to add an arbitrary constant at the end, but we never get to the end, and so we better add the arbitrary constant at the beginning. And this very nearly gives us a power series for the arctangent of x, the only problem being that annoying constant c. It would be lovely if we could get rid of it, and it turns out that we can. If you plug in the value x equals 0, we get that the arctangent of 0 is the constant, plus 0 minus 0 cubed over 3, plus 0 to the fifth over 5, etc. And all those values all have some power of 0 in them, so they're all equal to 0. And the arctangent of 0 is 0 as well. And that gives us that the constant is equal to 0. And so we've determined a power series for the arctangent of x. The arctangent of x is x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7th, etc. and on forever, provided that the absolute value of x is less than 1. Let's consider what happens at x equals 1. We get the arctangent of 1 is 1 minus a third plus a fifth minus a seventh, etc. And although it's not guaranteed by the theorem, this power series converges by the alternating series test. This is an alternating series, and the terms are decreasing and going to 0, and so this converges. And the beauty of that is we know the arctangent of 1. The angle whose tangent is 1 is the angle whose sine and cosine are the same. That's pi over 4. And so pi over 4 is equal to 1 minus a third plus a fifth minus a seventh plus a ninth, etc. Or multiplying both sides by 4, we get that pi is equal to 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths, etc. On and on and on forever. We have just come up with a series representation of the number pi, which is to say that one way to define the number pi is the sum n equals 0 to infinity of -1 to the n times 4 over 2n plus 1. And just for entertainment, it does turn out that this definition of pi is better in some ways than the usual ratio of the circumference of a circle to its diameter. The idea that the ratio of the circumference of a circle to its diameter is a constant, and in particular the constant pi, turns out only to work in Euclidean geometry. If you look in other geometries, it is no longer the case, and yet you still can have a number pi so long as you define it like this. Okay, there's homework on operations on power series. Have a lot of fun with it, and I look forward to seeing you in class. Bye.